And Brahe said, no, but you may sweep my floors. No, just kidding. But basically, Brahe put him to work, gave him a little bit of data, a little bit of data, a little bit of data. Eventually, Brahe dies. Kepler gets all the data, because he inherits everything, right? He gets all the data, and fairly quickly, in the space of, I think, a year or so, he comes up with these 3 laws of motion, okay? Now, let's just go into them here, okay? The first one is that orbits are actually not circles. In general, orbits are ellipses, okay? Or ellipses. Ellipses, plural of ellipse, okay? They are ellipses, okay? Now, remember that an ellipse has 2 focal points, and the circle is a special condition where the 2 points are copointular, yes? There's collinear, there's also copointular, isn't there? There's not really, but there should be. These are, I'm going to make a list of geometric terms that really should exist, right? Like how about an angle that adds to another angle to add to 360? To add to 180 is supplementary, right? To add to 360 is wholementary, right? Smaller than 90 is acute. Smaller than 45 is adorable, right? Yes? Okay. You know? Okay. Now, here's the crazy thing. Do you guys know Ptolemy's model? Are you aware of Ptolemy's model? Ptolemy came up with a model to explain the motion of the planets based on the notion that they all go around Earth. Yes? It was a vastly complicated model. It had these, and it was an actual mechanical thing. He actually mechanically modeled this thing. There are actually these like analog mechanical computers that would predict the position of the planets in the sky. And the crazy thing about it was that when Copernicus came along and said, no, everything orbits the sun, his model worked worse because he made his orbits circles. And they're not circles. And so Copernicus, is the sort of funny thing was that when Copernicus came out with the right idea, his model worked worse than Ptolemy's. Everybody knew that Copernicus was right, that was a simpler explanation. But when they wanted to find out where something was going to be at a particular time, they actually went back and used Ptolemy's model for a while. Isn't that funny? That's a little funny, isn't it? It's like we know it's not right, but it works so well. Yeah? Okay? Well, as soon as you make Copernicus's model have elliptical orbits, then everything works just fine. It's all hunky-dory, right? So this was the missing thing, the missing link, right? The Rosetta Stone, the whatever it was that we needed to actually fill in the thing. Okay? And the central body is one of the focal points, and then the kids always say, well, what's the meaning of the other focal point? And the answer is, I don't know. I don't know what it is, okay? There's nothing there, okay? The second one is said in a very convoluted way. I can explain it in a much simpler way, but let's go with what Kepler said because it's of historical significance. If you had a large oval pizza, okay, this will explain it to you, okay? This slice of pizza here, let's suppose this is the position of the planet in one instant, and then this is the position 10 minutes later. There she is, all right, okay? That's an equal amount of time. If it's close to the planet, here it is now, here it is 10 minutes later. Isn't it, by the way, moving faster when it's closer to the planet? Yeah, there we go. So what that means is to sweep out this area, if this area here is equal to this area, right? If the small thin slice is as big as the short big slice, right? Wide slice, then it's got to be going faster here, yes? Okay. So the simple explanation of the second law, of Kepler's second law, is that it just goes faster when it's closer to the planet. Yes? That's not so bad, is it? That's easy, okay. Now the crazy thing is that he actually derived this before there was calculus. To prove it, you need calculus. It's an exercise that you'll do at some point in like differential calculus, calculus 3. Your second year of calculus, that'll be like in the book, show this, right? Okay. Now, this is the last one is the formula, and then when we say Kepler's laws, and the book gives you some problems with Kepler's laws in it, okay? That's the thing you're going to use, right? Is that he showed that the ratio of, if you take planets orbiting the sun, if they all orbit the same body, right, and you've got the sun, you've got planet 1, right, and you've got planet 2, okay, so say Earth and Mars, right, okay, Earth and Mars have their own radius of orbit and they've got their own period of orbit. And if you take the radius and cube it and divide by the period squared for one of the planets, it's equal to the radius of the second planet cubed over the period of the second planet squared. That's sort of obscure. How do you show that without Excel? Can you imagine that and figuring this out with like an abacus or what? I don't even know. Did they have computational engines, like little things they could turn, or slide rules? I mean, I just don't even know. I should know. But he figured this out, right? And did he try like r squared over t to the third first, or r over t, and I don't know. He had years to do it. You could figure it out if you had the data, right? And you could just try all different powers of it. You could probably figure it out in an hour with Excel. If you knew there was some relationship like that and looked for it, right? Okay. So when we solve problems, we're going to do like an example problem here. When we solve problems, that's what we're going to do, is we're going to use that. Are we ready for the next one? So I think the next one's like an example of this, right? So Mars is 1.524 astronomical units from the sun. If our year is 365.26 days long, how many Earth days is Mars's year? What is an AU? What? Yeah, it's an astronomical unit. What is an astronomical unit? It's the distance between the Earth and the Sun. And the crazy thing about astronomical units is this. For the longest time, we knew the exact distances of the planets from the Sun in astronomical units, but we had no clue what an astronomical unit was in years, or I'm sorry, in feet, right? We couldn't figure it out. We didn't know what it was in meters. We didn't know really how long it was, okay? An astronomical unit was just something, and we knew that Mars was 1.524 times as far from the sun as Earth, but we couldn't tell you how far we were from the sun, right? And it wasn't, we'll actually go into how it is that we figured that out next year, if you take physics, how it is we figured out what an astronomical unit was, the first approximation, and then to actually figure it out very accurately, you have to actually wait till Venus, I think it's Venus, transits the sun. Venus will go across the sun, or maybe it's Mercury, I can't remember, okay? So let's set this thing up. This is our Kepler's equation. I'm going to make the planet number 1 be the Earth. Right? I'm going to make this guy be Mars. Okay? And let's just set this thing up. I guess the way I've got it set up there is that this is Mars. So let's make this guy Mars. Let's make this guy Earth. Right? And then you just fill in what you know and solve for what you don't know. Okay? So radius number 2 is 1 astronomical unit exactly to the third over 365.26 squared, right? And then this is Mars's situation. Mars is 1.524, and that's squared over whatever its period is. Oops, sorry, this is to the third, and then that's squared. Yeah? So take your calculator right now, even if you haven't been paying attention and have been sort of chatting the whole time. If you would take your calculator right now and solve that for the t, you'll be forgiven for chatting while I'm trying to teach. You might want to switch these guys, right? You actually might want to just sort of flip it around. It's in the denominator, so it's sort of like a little bit difficult to find, right? Isn't that, if I solved it for T1, I'd slide that guy over there, this guy up here, this guy down here, wouldn't I? You could do, yeah, you could. Open your eyes. You guys get 687.19.